So in this case, we are going to consider the properties of our gas turbines. Remember from the introduction, we managed to work on the basics of the theory that you need to understand, focusing on the gas turbine, the types of gas turbines, and we referred to the two types of our gas turbines, which is the impulse, all right, and also we have got the reaction turbine. So in our class, we are going to focus on the impulse turbine, all right, which we had previously that the nozzles direct the gas onto curved blades fixed to the perimeter of a wheel. Remember, that is what we had on an impulse turbine. We saw that here it is directly the nozzles that will direct, all right? The nozzles direct, all right? They direct the gas onto curved blades, onto curved what? Onto curved blades fixed. They are fixed here to the perimeter. Fixed to the what? To the perimeter of a wheel. This is what we had from our explanation, all right, from the previous class that we had. We considered this as part of the impulse turbine. There are a lot of things. The blades are shaped like buckets and asymmetrical, this and that. So in our class, like I said, we are focusing on the velocity diagram for impulse turbine. All right. Where in this case, all right, I'm going to show you this illustration that we are going to work with, focusing on our impulse, all right, turbine, which is the velocity diagram. So what we are going to consider in this case, we've got this part where we have got our inlet velocity diagram, and also we've got the outlet velocity diagram. And this presentation is the one that is the same as what we have here combined together. All right. So from what we have on our inlet velocity diagram, we have got from the nozzle, all right, and this is the entrance that we have at an angle of what? At an angle of alpha. And the velocity that is affecting being what? Being our V1, which is the absolute velocity of the gas. All right, so this is what you're going to have. And here, obtaining our blade speed or the blade velocity or the wheel speed. All right, then we consider also here our VR1 on the inlet, which is now the relative velocity of the gas. And here VF1 being the flow velocity. All right, then on this we have got VW1, which is representing the wheel like this, velocity. All right, here I said on this U, it is the wheel like wheel, right? Wheel like this, all right? Or the blade velocity, all right? So that is what we have from that end, all right? So the description from what we are going to consider is direct, guys, all right? From the first, from our inlet, this is what we have. So it is the one that is being combined now on the other side from where we are seeing here the outlet velocity diagram, all right? So both now being combined together, giving us this. So here what we just had on the inlet is the same thing that we are having on the what? On the outlet. Only that we now have VR2 where we had this was V1. So this is now our VR2. This is our V2, where we had VR1. Okay, so you must be careful about that. Our flow velocity on the outlet, we have our velocity for the wheel velocity, this one. Then we've got the blade velocity. So I'm going to consider this part of the angles, all right? The part of the angles, which is very, very important for you to know the angles that we are going to work with, all right? Or the angles that we are going to consider for our revision purposes, all right? We have got alpha, all right? So this one is alpha, the angle alpha. All right. Then we have got theta. So we also have our theta here. All right. Our angle theta. And we also have beta here. We also have our beta and phi, in this case, this one. All right. And angle what? And angle phi. So those are the ones that I'm going to consider differing with your textbook, right? They can use in different ways. So in this figure that we are seeing here, the blades of the turbine rotate here. The blades of the turbine, they rotate with a velocity, which is what? Our peripheral velocity U. The mean rotational speed of the turbine. They rotate at that. So that's the gas jet here with the velocity V1. So this is our gas jet, which what? Velocity V1. Issues from the nozzle. So it is what? From the nozzle at an angle alpha, at this angle alpha. So from the nozzle at an angle what? At an angle alpha. So that's when you consider that angle alpha, it is our nozzle angle in actual sense, all right? So it is the gas that is velocity V1 issues from what? From the nozzle with angle alpha. So this part or the gas that we have, it strikes the blades and enters at an angle. The one that we have here, it strikes the what? The blades and enters at an angle theta. So it is entering now the blade. So that's at this point we have the blade point. All right, let us just call this one our blade point. So that is entering there at angle theta. It enters at angle theta. So the angle theta is now the inlet angle of the moving blade. It is the inlet. All right. We're going to talk about this later on. That is the inlet. At angle theta with the relative velocity at that angle theta with the relative velocity what? VR1. That is what is happening. So if we consider this, we are going to see that the jet velocity, which is V1 here, is resolved into two components. So this V1 is now given into what? Two components, which is the tangential component VW1, okay, and the axial component, which is VF1. This, like, if we take the whole of this part from our diagram here like this. So we are simply saying this V1 is now considered or referred to, all right, that is considered in terms of two components made up of what? VW1, the whole part here, VW1 here, and what? And the whole of this part here, which is what? Our VF1 for the flow. So V1 is taken as components of these two, all right? Where in this case, the tangential component All right, VW1 is the tangential and VF1 is the axial what? The axial component. This one is what? Our tangential component. So that is the tangential components are referred to as what? Wheel components. Those are the wheel components, the wheel velocity. All right, which is what? Wheel velocity 1 and this one wheel velocity 2. So these, the tangential velocity, if we check, they are simply parallel to the direction of what? Rotation. They are simply parallel to the direction of what? To the direction of rotation. That is what we can see. Okay? So that is what we have. And also, talking about the axial components, we have got VF1 here, and we also have VF2. So these axial components do not do any work on the blades as they are perpendicular to the direction. If we check, this is going up, the direction of rotation is this, so they are perpendicular to the what? Direction of what? Rotation. So they do not do any work. So that is what we actually have on this part. Then, if you consider on the other hand, the jet glides over the inside surface of the blades, entering and leaving the blade tangential without shock, but has to overcome some friction. So that's at the exit now. The gas exits at what? A velocity VR2. So it exits with this velocity VR2, the relative velocity. All right? That is at the exit, and the angle what? And at angle phi. So this is part of the exit. It is exiting here at what? At VR2. This is our VR2 at angle what? At angle phi. So this angle phi here is the exit. It is the exit. Remember, it entered, it strikes there at the blade, at the inlet, then it exits as what? As VR2 at the blade, at this blade exit, which is our phi. All right. So that is what you're going to have. Then the gas leaves the blade with an absolute velocity, what? V2. So that's now the absolute velocity at the end is considered, and at an angle, what? At an angle beta, which is when the direction of gas leaving what? Let the absolute, they were talking about the absolute velocity at the angle beta v, this one, the v2 and what? And beta, that will be the direction of what? The direction of the flow of the gas at the exit is now exiting with that velocity at an angle what? At an angle beta. So all this is going to be represented, like I said here. So we've got the first triangle representing the part of our inlet. All right. So let's say we've got points A, B, C, and this is point D. We can see that, all right, let's call this one like this, A, B, all right, then C, D, whatever. Here, you're going to name the way that you want. You can name this one C, and you name this one E. So if we are to consider A, B, C, this triangle is the inlet, and from A, B to D, we have the triangle representing what? The outlet now. This is what we have. Okay? This is what we have at the end. And you must take note the flow velocity VF1 and VF2, they are at what? 90 degrees from the point C vertically up at what? At 90 degrees. You must draw a perpendicular line. And from these points, let's say this is A, B, let's say this is point E. From A to E, this point, this line is now representing VW2, our wheel velocity. And from A to that point at the end, that's our wheel velocity 1, which sum up to give us the total what? To give us the total wheel velocity, like this. which gives us the total wheel. If we measure, all right, what we have from this point at the end and this point at the end, if we measure that, that is going to give us what? The total wheel velocity. So all these are represented here if we are to take properly, all right? One is for the inlet, two is for the outlet. So U is the blade, which is our peripheral velocity of the turbine in meters per second, this U that we have here, which can be calculated from the diameter. All right, V is going to be for the absolute velocity of gas. All right, so we have part of our V, V2, V1. Those are absolute what? Velocities on the inlet and on the outlet. Then we have got VR, which is relative what? Velocity of the gas. So we have got VR1 and VR2. VR1 affecting the inlet of the blade, VR2 affecting the outlet of the blade there at angle phi. All right, that is what you're gonna have. And another part, VW, this one is simply the wheel velocity, VF, the flow velocity. We saw the part of our VF affecting the flow velocities, VF2 and VF1 there. Those are flow velocity. All right. Then we have got alpha representing the what? The nozzle angle. So here part of our nozzle angle alpha, which is from the turbine point, our nozzle angle is what? Is alpha. And another part is theta, the inlet angle of moving blade. So theta is one, the inlet, where the one at the exit is going to be angle phi. So I'm going to use angle phi like this, the outlet angle. All right. Then B is the direction of gas leaving what? Blade. So like I said, for the absolute velocity, our beta, I mean, not B, but beta there is what? The direction now of gas leaving blade. So basically, this is what you're going to have. If you understand what is happening here, the entrance, this is the inlet, and this is part of your what? This is the part of your outlet velocity, just that they are now combined together to give us this an identical diagram that we are having here. So that is what we are going to consider. And sometimes we can have a condition where where there's an absolute discharge. When there's an absolute discharge, your beta is going to be equal to 90 degrees. We're going to talk about that as a separate, like doing examples. You're going to do an example where beta is 90 degrees, then you know that it's an absolute discharge, or it is it discharges axially. All right, so this is part of impulse turbine. We are going to consider another part, which is of the reaction turbine. So the reaction turbine has got its own properties similar to this, but all these, like the terms, this and that, they are not going to change. Only that the diagram is the one that we consider. So from other textbooks, they're gonna use C for velocity, where we've got C, like CR2, CR1 as velocities. All right, or you can just consider what VR, VF, like, so that we do not miss any part. We can consider this. All right, so that is basically what you are going to have, and also the calculations thereafter, which is important from this diagram that we are seeing here. All right, we measure what we can measure because it is drawn up to scale. So we can measure where we can measure, we can do calculations mathematically because these are simply triangles that we are formulating. And if we check others, we have got right-angled triangles that we are forming. So we can even use trigonometrical ratios where it is applicable in terms of what? In terms of your calculations. And the drawing part, how to have this at the end, differs with the question. Sometimes you can be given information that leads into the first triangle. You can be given information that leads into the second triangle. So you work with the given information, just have a sketch. From that sketch, you use it to draw the diagram, all right, from the given sketch. So we're just going to work out questions so that you know basically how to attempt those typical questions. But in any part that you have, try to work with a sketch. Work with what? The sketch. So let me just consider this part of your calculations, which is also important. Our calculations that we are going to consider for impulse turbines. We have got the first one, which is the blade velocity, U. Remember, representing what? Our blade velocity. It can be calculated when we are not given that. So that's our peripheral velocity, right? Is this thing of pronunciation is something else. So that's our U there, representing what? Our blade velocity. Or they can consider this one as the wheel velocity. Again, all right, that's can be calculated from diameter. So U is equal to pi dn over 60. All right, to convert this one to revs per second, n must be revs per second. So you have to divide by 60 because you are given this one in what? In revs per minute. So we have to convert to per second by dividing by 60, and we want to obtain what? Meters per second. So that is what basically you're going to have, where D is simply our rotor diameter in meters, and N is going to represent our rotor speed. So this one is simply our rotor speed in revs per watt, in revs per minute. And another part that you are going to consider as part of your calculations is going to be the axial thrust. All right, the axial what? Thrust in this case, all right, or force. It is actually a force that you're considering there, axial thrust or the axial force. So I'm going to write that one as FC. So FC is going to be the mass rate into VF1 minus VF2, the flow velocities. All right, remember VF for the flow velocity. So your answer in what? In Newton. So that is it. M is simply for the mass. All right, so that is the mass rate that we're given of gas. So this one is simply the mass flow rate of what? Mass rate of gas. So definitely it's going to be kilograms per second in order for us to obtain the Newton. So this must be in kilograms per watt per second. Whilst these velocities are in meters per second, we are going to obtain the axial thrust or the axial force from there. And another force, another part is going to be force on the blades. Whenever we consider force on the blades, that's our tangential velocity. That's our tangential force, I mean. That's our tangential force, which is F tangential. All right. So remember, we referred to this part of the tangential velocities, all right, before when we said we've got the components, I mean the tangential component, where our tangential component is what? Is the VW1 and what? VW2. So meaning to say the tangential force has to be taken from those tangential components, VW1 and what? VW2. So it follows that FC is equal to the mass rate of the gas that we had before into the sum of VW1 and what? VW2, our wheel velocity, all right, in meters per second. But remember, this here represents the sum. The sum represents the total, all right? That's our total wheel velocity, the change in wheel velocity, that's our total. So you can simply put that one as the what? As the change or the total wheel velocity in place of this. All right, so that is basically what you're gonna have. So that's, you can simply write as FC is equal to the mass rate times what? The total wheel velocity. All right, the change or total, that is the one that you're considering. So this is going to give our answer in newtons. Okay, so that's what you're basically going to have, and you're going to consider this as part of your calculations. And you also have the work done on the blades, which is actually, I'm just going to consider this one, the work done per second, per unit time. So work done on the blades, all right? No problem. The work done on blades, when it is work done per second, it represents power, joules per second, that's a watt. So it is simply equivalent to power. When you're calculating work done per second, you are calculating what? Power. So that is going to be from the tangential force. Remember, force times velocity. If you consider force times velocity, it gives us what? Power. Power is equal to force times velocity. So the force is going to be our tangential force, which is Fc. So Fc is equal to this. So that's the mass rate times what? The total wheel velocity, all right, times what? The velocity. In this case, our velocity is going to be of the blades, which is what? Which is u. So this is going to give us power, force times velocity. So that's going to be in what? In joules per second. So that's work done per second is power. So that's joules per second, which is equivalent to a watt. All right. 1 joule per second is equal to 1 watt, remember. So that is calculating power at the same time from that formula. And another part is going to be the blading or diagram efficiency. The blading or diagram efficiency. Diagram efficiency. So that is can be calculated. Our blading efficiency can be calculated from the formula. That's 2 times u, which is our blend velocity, times the total wheel or change in what? Wheel velocity over V1, the absolute velocity at the inlet, V1 squared, all right, times 100%. So we have these formulas, just issue of applying them properly. So we can actually see that here we have work done per second over input. So it's simply work done power over what? Over input energy. Power over what? Over input energy per second. It's going to give us what? It's going to give us efficiency. So you're going to consider power over that. Or from the calculations, we can simply consider it from here, right? So that is what we have as the blading or diagram efficiency. Then another part can be the relationship between the relative velocities, or VR here, VR, all right? So the relationship between VR1 and VR2, those relative velocity, they give us the blade velocity coefficient. So it follows that we can determine what we refer as the blade velocity, the blade velocity coefficient, which is K. So that's our blade velocity coefficient. K is equal to VR2 over VR1 from the relative what? Relative velocity. So from here, it follows that VR2 is simply multiply this. So that's VR2 is equal to K times what? VR1. If you want to calculate VR1, is just going to be what? VR2 over what? Over K. So you can calculate one from another. From what you're given, you can calculate another part. If you're given VR1, and that blading velocity coefficient is given, you can calculate VR2 from there. All right. And also another important aspect is going to be on the loss in kinetic energy. All right. So the loss in kinetic energy, all right. The loss in what? Kinetic energy. The loss in kinetic energy due to blade friction. So this is due to blade friction. Right, they are going to ask about this one. So that's EK. Loss can be calculated from the mass rate into the difference here, VR1, the relative VR1 squared minus VR2 squared, which are the relative what velocity. So this is going to give us the loss in what? In joules. That's VR for the relative velocity of the gas. So basically, these are the formulas that we are going to consider, and any other adjustment that can be taken. Remember, like I said, we are dealing with the triangles, and some of these triangles are right-angled triangles. So other calculations can be done mathematically. We can have those calculations depending with what you are given. I just want you to consider, just for an example, let's say I've got this triangle A to C to this point like this. Let's say this point is F. From A to F to C. It is a right-angled triangle at angle alpha like that. It is a right-angled triangle like this. This is A, F, and C. And it is a right-angled triangle at F, and at A, that's where we've got our angle alpha. Where A to F, this part A to F, we've got this U and this other distance here that we do not know, but F to C represents our VF1, and A to C represents what? Represents our V1. Don't we have a relationship from angle alpha? This is what? Our opposite. This is our hypotenuse. So it follows that the sine of theta from our SOHCAHTOA, where there's opposite, the sine of alpha here is equal to the opposite, which is VF1 over the hypotenuse V1. So you see, guys, if we have that angle and we've got VF1 or we have got V1, we can calculate VF1. Sometimes from your calculations, if you have to consider this other side, we have the same condition from this angle phi that we are having like this, from this right angle to triangle like this, we've got the angle phi, and from this point up to this point, all right, and here from B to D, that's our VR2. From E to D, that's our VF2. So we can actually work out from these two and find whatever that you want to calculate from there. If you even want the whole distance from here to here, you can have that. Then subtractions can be done because we have the other values. So we can manipulate from what you're given, work out from the right-angled triangles. We also have them here. This one's a right-angled triangle again from BF to C. This one, it's a right-angled triangle again that we are forming at an angle theta here. All right. Where from F to C, that's what we have got our flow velocity. Then from B to C, we have got our relative velocity. So we can use that with what we are given. We've got opposite hypotenuse here. There is beta on the other end, forming a right-angled triangle. This is our angle beta, and we've got the flow velocity. And from A to E, which is what? Our VW2. So we can play around that right angle triangle with what you're given, find what is missing from your right angled triangles, working with trigonometric ratios. Remember, we have got part of our trigonometric ratios and so forth. So this is just a basic of what you are going to consider thereafter. So please do revise all the basics, all right? The terms, their meaning, what is it that you are representing from each term? Then consider examples thereafter. How to construct depends with the information given. There is no way that you're going to say, this is the only way, follow this way, like this, like this. No, it depends with what you're given on the information. Simply have a sketch first, all right? Have what? Have a sketch. From the information that you're given, you must have a sketch. Then you draw this one according to scale. This part after the sketch, you must draw exactly according to scale. According to scale. So that is what you're gonna need. And for drawings, for centimeters or those millimeters and so on, we can consider maybe 1 decimal place. That is something that we can measure properly. Like let's say we have got 5,1 centimeters. You can use as 51 millimeters. It is easier because on your ruler you also have millimeters. So just multiply by 10, you've got millimeters. So it is better that you work with 1 decimal place when you are working with what? When you are working with the measurements in centimeters or millimeters, whatever that will be given. The other part, round off as usual. You can just use your 3 decimal places. But for those ones that you're going to measure in terms of construction, it will be difficult for you to construct 5,125. But if you have got 5,1 centimeters, you know it's 51 millimeters. You can measure 51 millimeters direct with the ruler. So that is what I'm trying to say. So let's do revise. Let's do revise. We're gonna continue from here in the next class, working with the constructions, of which I've already done some question papers, just that you guys wanted a basic understanding. So from that introduction that we had, we need to correct, we need not to correct actually, but to adjust these terms to what we had, I mean, from the question papers that we're dealing with, all right? Maybe sometimes we're using the letter C for velocity, all right? Then we have now VR this, VR1, VR2. It is one and the same. So it depends with the textbook that you are using. So yeah, I'm just using this one according also to the updated syllabus, so that when you are doing your revisions, you know what you're working with. But as for the angles, I'm not going to change. I'm just going to work with these angles. As for me, theta, phi, alpha, and beta. Those are the ones that I'm going to use so that we will be together when we are constructing these diagrams. All right. So that is it, guys. Till we meet again.